And I will return godliness to you.
That's a heavy burden.
Yeah, be sure you're still, looks like you're still sharing your screen just fine.
That's a tongue twister.
Go ahead and scroll up or down just to be sure it's actually, yeah, okay, it's working. You are back in charge.
Okay. I was going to try to look at my old textbook for a better explanation of what a PDF is, but I don't really. Again, this is an engineer class, not a math class, so I think we'll be good. So we're going to be looking at the question of how close is close. Well, that is going to be a question you ask yourself continually for the rest of your career. It might not always be the word close. Sometimes it'll be how small is small, how large is large. But the answer to that question is there really is no answer. You can't have 100% in everything you want. So we have to decide on what level of goodness of fit we're okay with, and what are the standards, and how do we get those? So back to regressing linearly. That seems to be our tasks in life. But as far as tasks go, at least it's linear. What is linear regression? It's a basic predictive analytics technique that uses historical data to predict an output variable. In layman's terms, you have data. Data forms some kind of pattern. I've been watching a lot of Star Trek, so I get those two mixed up now. The data forms some kind of pattern, and you want to use that pattern to predict an unknown variable that would be, I wouldn't say it's in your data set because then you would know it, but it's in the same field. Now this thing you're trying to predict, it doesn't always have to be in the future. Let's say you're wanting to predict something. Predict is a strange word to use in this context, but you don't know the concentration of, I forget exactly what it is. CO2, the acid it makes, carbon dioxide. It makes an acid in soil. You want to know what it was in 1660 or whatever, whenever it was when Krakatoa went off. You don't have a measurement of it, but you have a measurement due to some ice measurement stuff you took in a couple of years, before and a couple of years after. You can predict what it is by using that pattern. Why do we need linear regression? It lets us explore the relationship between predictor and output variables and predict the output variable based on known values of predictors. So I have my data of my X is what you're used to. You can call it your X variable, usually input variable, but it's really technically called the predictor variable. I've got a bunch of these, and based on the relationship between the predictor and the output variable, I can predict what an unknown variable is going to have as an output. Yeah, for a second there, my camera list only showed like 3 people. I thought we crashed or something. All right, so how does linear regression work? To estimate y, which is our output, using linear regression, we assume the equation that our y estimate is beta times x, which is our predictor variable, plus some alpha. Now, beta and alpha, they're numbers, but they can change based on which method we're using to calculate them. So our goal is to find statistically significant values of the parameters alpha and beta that minimize the difference between the true y and the y estimate. Now remember, we can't actually know what the true y is. The only way to know, especially in any kind of non-trivial example. So I could, Russian roulette or a D6 or even a deck of cards. It's kind of a trivial example of what's what is the true likelihood of stuff using these things? So pulling the trigger, shuffling the cylinders, so on and so forth. I am constructing that scenario for you. And it's useful because it lets us talk about other methods. But when you're using these methods in what's commonly referred to as real life, it's nearly impossible to really know what the true relationship between the predictor and the output variables are, especially because there's probably going to be more than one predictor variable. The only way to truly know what it is to lift up, tear a hole in reality and look at the hardware of the universe, and we can't do that. We're humans. So what's the next best thing? Well, we want to minimize the difference between the expected and the true. Now, how do we minimize if we can't know what the true output is? Well, we can't know exactly what it is, but we can calculate the probability density function for it. Meaning, think back to
chocolate or vanilla?
Duh, chocolate.
Oh, and
Well,
while
that
we're
was
eating
interesting.
together,
Michael Skiles, you were unmuted. I did you a favor and muted you, and I suggest you cut down on the ice cream. It's not good for you. All right. Where was I? All right. So we can calculate, at least for a normal distribution, the quartile. So we can figure out the, oops, that's terrible. It's not even a line. We can calculate the standard deviation and variance for our distribution, even though we don't know what the distribution truly is. And we can draw these lines in our distribution saying, all right, one standard deviation away from the mean, we have a 68% chance of finding something in this area, and so on and so forth. We can do that with two standard deviations, which gives us 95, I believe. I think it's 95. So using these, this is the closest tool we have to having the true distribution. And so with this PDF, this isn't technically the PDF, but it's what I can get us. We can say, all right, here's my estimate. Well, let's check it against my model. It seems to be, it's not giving me anything weird. Every value I'm getting is within the 95% bracket. Okay, that's good. Let's try taking it to the 68% bracket, and we can refine it, so on and so forth. All right, so if we're able to determine optimum values of these two parameters, alpha and beta, now what do we mean by optimum? That's the $1 million question. How close is close? That's the hard part. If we are able to determine the optimum values of these two parameters, then we'll have the line of best fit that we can use to predict the values of y given the values of x. How do we estimate the coefficients? Well, we've been using a method called ordinary least squares, but that's not the only way. What's the least squares? Well, it's pretty simple. At least it's simple to explain. You've got points somewhere, and you've got a line. Measure the distance from the line to the point. Take the square of the length, sum them all together, take the square root, and divide by how many points there are. And we want to minimize that number. All right. So when we discussed the probability density function for the normal distribution? Probably not. I remember this from stats because when you take stats, depending on the version you take, they're going to, the beatings will continue until memory improves, pretty much. This is going to get beaten into your head until you see it in your dreams. So yeah, this is the probability density function. I was going to take some time to explain what the heck is a probability density function. Why do we even call that? But suffice to say, this, for a normal distribution, this function here. So you notice the standard deviation sigma we have, and we have mu here for the mean. those are going to be some inputs, and we have X, obviously the function's over here. This describes how the distribution behaves, which will let us calculate those, is a value in this 95% area. Now, every distribution has a different, well, I guess that's technically not true. A distribution can have a different probability density function than this one. I wouldn't expect the Poisson distribution to have the same probability density function. In fact, it doesn't. But every distribution has a PDF, and you can use it to get the parameters that we need in order to do our linear regression. What this is telling us, it's the probability our sample X from our random variable X. Now, keep in mind, these are two different X's. How do I, so when you're really using a probability density function, I think it's changed. Oh, I didn't draw, there we go. The way it's gonna look is probability that, which way is it? I think little x equals big X. Because this is your sample. So what's big X? Well, it's my D6, throwing my fair D6 on a table and measuring the outcome. Okay, that's nice. Doesn't tell me how many times I did it. My sample is, well, how many times did I do it? My real world throwing of my die onto the table and measuring the outcome. Does the outcomes of me throwing it onto the table 1 time, 5 times, 10 times, 1,000 times, does it behave as the distribution for my D6 is supposed to? Those are usually the questions we kind of ask. That's the difference between sample X and a random variable X. Okay. So it's the probability our sample X from our random variable X when the true parameters of the distribution are mu and sigma. Now, what do we mean by true parameters? We're saying these aren't the estimates. We're saying these are the real, open up the panel on the universe and figure out, okay, what's the mean and standard deviation for this distribution? Now, we can't just peek in there and see it, but we can say, well, let's assume it's this. Well, that's not entirely correct, but it's closer. Let's assume it's this. And that's kind of how we play the game. All right, that's a whole bunch of gobbledygook. So let's look at an example because those are easier to work with. Let's say our sample is 3. What's the probability? It comes from a distribution. We're talking about normal stuff here, normal distributions. What's the probability? It comes from a distribution with mu of 3 and sigma of 1. What if it came from a distribution with mu of 7 and sigma of 2? Now remember, we're talking about means and standard deviations here. Which one is more probable? The 3 and 1 or the 7 and 2? I don't know. Well, luckily, this is an engineering class, so we don't have to do any calculus. Well, I guess we wouldn't be doing calculus, would we? Maybe. We don't have to derive this equation. We just have to use it. So I'm going to load up my very useful NumPy and Pandas, always want those. And we're going to be using Skippy to talk about the PDF for the normal distribution, because what it'll let you do is it just has a function. It's the PDF for the normal distribution. It takes 3 arguments. You've got your sample, you've got your mean, and you've got your standard deviation. I believe this was the other class that I had a question about yesterday, but it's worth talking about because the question is, they went and looked up the function to do a classification, which I think we do at some point in this class. If not, we've already done it, but they went and looked it up. Cool. They got a function. Cool. All right, nice. What does the function do is the first thing I asked. No clue. I don't even know because I'm just looking at it. Now we can guess that this is the PDF for the normal distribution. What's the point I'm getting to with all of this? Well, the Skippy normal PDF, I need to know what the inputs to this thing are. Well, that's pretty easy. Let's go look it up. Skippy norm PDF. It even said stats for me. All right, this looks like the official documentation. Let's see. Should be a PDF. Right here. So the reason I'm taking time to point this out is because now I know exactly what the inputs to this function can be. If you don't know what the inputs to your function are, you're gonna struggle. So I encourage you to take I don't know, it took me what, 30 seconds to look that up. When you're using a new function, look up the inputs. That way you can, it's like, oh no, I got 3 inputs. Where do they go? This is the order they go in. All right, so we got sample size 3, a mean of 3, and a standard deviation of 1. So what is the likelihood that our sample of 3 came from this? And this is going to be difficult for me to draw because I don't visualizing. It'd be easier for me to just plot. Well, I wouldn't say easier, but we've got 2 normal distributions. Let's say one looks like this and one looks like this. One's flatter than the other. I can say that the standard deviation here will, okay, I'll try to do a little bit better. We got our, that's terrible. It's tilted. We have our number line, and we have 2 normal distributions. The first one has a mean of 3. It's not a very good line, but that's okay. Second one has a mean of 7. Now, the standard deviation on the first one is 1. The standard deviation on the second one is 2, meaning that that kind of interval we like to draw is narrower for this one than for the other one. Now, this is not to scale. Now this one's going to be wider. So the question is, and there's a reason that Dr. Cleveland chose the exact numbers we're talking about here. This looks like a weird ghost guy. Our sample is 3. We pulled a 3 out of the hat, where the hat is stuff that comes from here. Is it more likelihood that it came from this distribution or from this distribution? Now, you can pretty much look at it visually and say, hey, it seems like this one's mean is a 3, and this one's way off at 7. And the standard deviations aren't anywhere near enough to get me a 3 from here. In fact, if I were to get a 3 from this one, that would have to be 7 minus 2 gets me 5, not enough. 7 minus 4 gets me 3, which means it's outside the 95% range. So just with that knowledge, I can probably say it's this one, gun to my head. I would say this one, but we can do better. I'm going to plug those values into my PDF function. All right. So the likelihood that the 3 is coming from this one here, we've got a 40% chance that it is in in this distribution. That seems kind of low, but these numbers can seem kind of weird because really what it's doing is, remember those intervals we were talking about? That's what it's looking at. And what's the likelihood it came from the other one? 0.02. So we have, let's say, a 3% chance versus a 40% chance. Which one are you going to go with? All right. So let's get rid of those. So according to that, it's much more likely that it came from the first distribution. The PDF equation has shown us how likely those values are to appear in a distribution with certain parameters. Keep that in mind for later. But what if we had a bunch of points we wanted to estimate? Let's assume we get a bunch of samples from X, big X, which we know to come from some normal distribution, and all are mutually independent from each other. That means that the second number doesn't depend on what the first number is, and vice versa. If this is the case, the total probability of observing all of the data is the product of obtaining each data point individually. This should kind of remind you of our class on probability, where we talked about the probability of multiple events happening back to back, i.e. the royal flush. No, yeah, EG is more appropriate. I usually don't say EG in speech. It's weird. Okay. So what do we mean by that? Well, let's take the easiest example I can think of. Flipping a coin. What's the likelihood that a fair coin lands on heads? Can someone tell me that? One flip, likelihood of heads. %50%. Okay. Okay, now what's the likelihood that I flip a coin? It's heads. I pick that same coin up, I flip it, and now it's tails. %25%. Why do you say that? Isn't it 50%? Isn't flipping a coin likelihood of tails 50%? I did flip it 2 times. So why do you say 25%? You're correct. I'm just asking why you say that. The easiest way I can explain it is what I think I've talked about in this class before, is using the idea of possible worlds. So how likely is it that we start out in the world we're in? 1. How likely is it that we flip a coin and it lands on heads? It's 50%. How likely is it that we flip a coin and lands on tails? It's 50%. How do I know that? Well, there's everything has to add up to 1, and there's only 2 worlds here. So they're equally likely. 1 out of 2. Okay. So we're either in one of these 2 worlds because I flipped a coin. We're no longer in the first one. All right, let's assume I'm in the first one. What's the likelihood I flip a coin and it's tails? Well, it's 50%. What's the likelihood over here that I flipped a coin and it landed tails? I flip a new coin and it's tails. Well, it's 50%. It doesn't matter what the previous values were. It's independent. Same likelihood for heads. So now that I've flipped the coin 2 times, as compared to where we started, which is here, which is 1 world. So what's the probability of being in the world we're in? It's 1. What's the likelihood that we're in this one? It's 1 out of 2 because there's 2. What's the likelihood that I'm in any one of these given worlds? Well, it's the whole shebang divided about how many worlds there are because they're all equally likely. It's 1 out of 4. It's the easiest way I can explain it. Could have just said where was it? It's on the screen here that they, yeah, it's right here. Could have just said that. I wasn't trying to interrogate you. I was just curious as to how you knew it, which kind of is an interrogation, I guess, but that's my job. All right. So example 2, what's the probability of 2 and 6 being drawn from a distribution of mu equal 4 and sigma equal 1? Well, let's find out. Seems pretty unlikely. We have a less than 1%, so 0.3% chance of both of these being drawn from a distribution of mean 4, standard deviation 1. Now, what would be some numbers here that would have a higher likelihood than 2 and 6? There's a really obvious number, but let's pick 2 numbers. What would I want to maximize the likelihood that they are drawn from our distribution? So give me 2 numbers and we'll plug it in. 5 and then 3 or 4. Yep, very good. 4 is the mean, so it's probably the most likely to happen, especially with the standard deviation of 1. And since the mean is 1, we're going to go to the left one or to the right one. Doesn't really matter. So I can't think of one. Obviously, the highest probability I can think of would be 4, but that's not very interesting. All right, what's the likelihood of this? We have a 9.6% chance that both of them come from it. It's a lot better. It's more than 10 times better. All right, let us introduce the idea of a maximum likelihood estimation, the MLE. It is used to specify a distribution of unknown parameters, then using your data to pull out actual parameter values. To go back to the pin, let's look at our linear model. So this is our linear model. Why is it our linear model? Well, the formula we have for y is, y is theta. Let's start with theta 0, x to the 0. I'll draw it out. This is going to be backwards from what it usually looks like, but that's fine. So y equals theta 0, and thetas are coefficients. X to the 0 plus theta 1, x to the 1 plus theta 2, x to the 2 plus so on and so forth, theta n, x to the n. This is a system. Now, why do we call it a linear system? Is because we don't go any further than this one here. We don't have any x squared. The furthest we go is x. So it's a linear system with two coefficients. And this epsilon here, not until, yeah, it is. Epsilon is almost always used as a symbol to represent error. So generally, when you see a new equation and you see an epsilon in there, it's probably talking about error. So really what we have here, and I could have just looked here, is y equals mx plus b, the one we're all used to. It's just that since we're trying to estimate stuff, we call these thetas. So m is our theta 1 and b is our theta 0. And then we have this epsilon out here, which is usually very small, but it's saying plus or minus something because we're estimating. And remember the topic of the lab, how close is close? Well, that's where we are. All right, so epsilon is the noise parameter. It's the error. It's basically why the points do not fall exactly on the line. The error for each point would be the distance from the point to our line. We'd like to explicitly include those errors in our model. One way of doing this is to assume the errors are distributed from a Gaussian distribution with a mean of 0 and some unknown variance. The Gaussian seems like a good choice because our errors look like they're symmetric about where the line would be. And small errors are more likely than large errors. That statement right there, it would take me the entire day to tell you why this is exactly true, but just take it on faith that, and from experience, you'll see, is generally when you get a good line fit, errors are small rather than large. Large errors are rare. There's a theorem about that, but we're not going to talk about it. Okay, so the model we're looking at here has three parameters: the slope and intercept of our line and the variance of the noise distribution. Our main goal is to find the best parameters for the slope and the intercept. There's not a whole heck of a lot we can do about the noise. Noise is noise. Let's rewrite our model from above as a single conditional variable, conditional distribution given x. All right, so we've got our model. We're anticipating a Gaussian distribution here. So we have our x, and we have theta 1, theta 0, and our sigma squared. This is equivalent to pushing our x through the equation of the line and then adding noise from the zero mean Gaussian. That's this one here, the sigma. Now we can write the conditional distribution. Remember the PDF? So we have, I'll write this here. Remember when you have, let's say, when A equals B, and I'm trying to do some magical algebra, if I have some C, and then I do some operations on C to make it, to show that it's equal to A, well, I can plug in B for A because A is equal to B. And that's exactly what we're going to do. I have normal of theta 1x plus theta naught sigma squared. Doesn't matter what these three values are. I don't know. That's the point. Don't know what they are. But yeah, this looks kind of familiar. We have our x and the values on it, and we have our theta squared. So the it seems that I have a normal distribution. Let's try carrying over these values into what the actual PDF is for the normal distribution. So let's do that. We're going to take our theta 1, theta naught, and sigma squared, and we're going to apply the PDF. So this is equivalent. Oh, I already said that. Now we can write the conditional distribution of y given x in terms of this Gaussian. It's just the equation of the PDF with our linear equation in place of the mean. So remember where we had sigma? Or wait, I'm sorry, mu. So mu is here, x minus mean. Yeah, I guess that's true. We're going to do here. This is our function for our line. The semicolon in the conditional distribution acts just like a comma, but it's useful for notation for separating our observed data from the parameters. Now, what the heck is observed data and parameter? And why is this guy spending so much time talking about math? Well, this is a math lecture. For some, that's unfortunate. It can be dry. I'm trying to do my best. But what is the difference between an observed data and the parameter? Well, that's what we were talking about earlier. Little x, big X. One is, take the panel off the universe, look inside. Oh, that's what it is. But we can't do that. And the observed data is, how you take a stud finder, put it on a wall, and you're looking for the wood. That's kind of what we're doing. The wood's in there somewhere. I can't see it. It's behind the wall. But I have a stud finder. How good's my stud finder? I don't know. It's a pretty good analogy, actually. How good your actual stud finder is, that's your error. Okay. So each point is independent. I'm surprised we actually talking about this. I like this. Independent and identically distributed. Now, as far as statistics go, if you have this condition here, your life is nice. It means all the math we're about to do is possible. And the reason it's so nice is not only you draw a card from 52 card deck, you put it back. That means the next card I draw is going to have the same likelihood. Not only that, it's coming from the same deck. So that means, you walk up to the card deck, you pick a card, you write it down, you put it back, deck gets shuffled. That means I don't even have to be in the room. I can just say the distribution function of the thing you just got looks like this. All of the students have the same one, so I can just sum them all together and I can go about my day. So we have IID, independent and identically distributed. So we can write the likelihood function with respect to all of our observed points as the product of each individual probability density. Since sigma square is the same for each data point, we can factor out the term of the Gaussian which doesn't include x or y from the product. So we're, let's see. I will do my best because I always hated it when there'd be a math day in whatever class we're talking about. And that's not the thing I hate. This is the thing I hate. When the instructor would just go on before people have a chance to figure out what's going on. And I understand this is essentially deriving an equation. So this is tough. I encourage you. This is pretty much the lab today. Stop me if you are lost or confused. So far, all we've done is we've got our theta 1, theta naught, and sigma squared. We plugged them into our PDF. We're not doing anything weird yet. We're about to start doing some stuff. So I'm gonna note them a little bit in red. I'm not digging it. Let's this should work. All right. So notice we have this spot here. what does this depend on? So like I've got my function. Well, let's not do that. Let's do f of x is, I don't know, 1 over square root of 2 pi times 61, this whole thing times x, right? I'm going to put in a number for my x. I'm going to get a value. I'm going to put another value in for my x. I'm going to get another value. Does this thing here, does this change depending on how my inputs change? If I plug in 1 for x, is the thing I'm multiplying my x by going to change as if compared if I put in a 2? Does this term right here depend on anything in my input? Rory says no, and you are correct. There's no x in here. There's a 2, there's a pi, and there's a 61. Those are all constants. So that means I can treat this, let's call this thing, I'll call it C for constant, C1. That means f of x is C1 times x, which means I can move C1 wherever I want. I can say x, C1, whatever I want to do. Now, the reason I bring that up is because we want to talk about this one here. Now, this term here, does it depend on anything in my input? So the term we're talking about is 1 over square root of 2 pi sigma squared. Probably should have drawn that bigger, but such is life. Does this term depend on anything in my input? So my inputs are here. Because what I want to do is I want to be able to move this around. So yes, Mateo says it depends on sigma squared, and in fact it does. So I guess we're out of luck. Except our inputs are independent and identically distributed. So we have a couple things. We have IID, and we know they're all from the normal distribution, which means this value never changes. If a value that can change, which input, so we'll call it an input variable. If an input variable never changes, what kind of thing is that? There's a word for something that doesn't change. It is blank. What's that word? Constant. Very good. So this is a constant. Sigma squared is a constant in this particular case because we have IID. So if it's constant, I can move this term wherever I want. Can I explain why it doesn't change, please? I will answer your question. Yes. There are two things that guarantee that sigma squared is never going to change. What is sigma squared? It is the variance for our Gaussian distribution. That is, in fact, I'll go up to exactly where it's defined. That way you don't have to just, all right. Let's assume there's some errors that are distributed from a Gaussian distribution with a mean of 0 and some unknown variance, sigma squared. So it's an unknown variance. But we're saying it's a variance from a Gaussian distribution. All right. So what we're dealing with is a Gaussian distribution. We plugged in the PDF. Sorry, I got an email and I blanked. All right, so we know that it's the variance of a Gaussian distribution, but we also know that every single input I'm going to give into this is independent and identically distributed. So we can, what that tells us from above is we can take the product of each probability density. That also means that this sigma squared is never ever going to change. Every time you're drawing from the same deck, it's been shuffled and it's the same number. So that's why. Okay. So we're going to do some algebra. What we're going to do is we're going to do the other thing that IID gets us, in that we're going to take the product of everything we're wanting, and we're going to insert it right here. That's what we're going to do. Well, really, we're not so much inserting it as we're taking the product of everything, and we're moving this out because it's just a constant. Okay. So as I was just saying, since sigma score is the same for each data point, we can factor out the term which does include x or y from the product. Now, x to the e, so everything in this term can't be factored out because it's x to the something. All right, next step is to do a whole bunch of algebra. We want to find parameters which maximize this function, which means sigma squared is not going to be changing, but theta 1 and theta naught are. So fiddle with them until we find the maximum we can. So let's do some algebra to make this a little simpler. Let's take the log of our likelihood. So that's the likelihood. Now, so this again, this is a whole bunch of algebra. The how did you think to do this is not the point of what I'm explaining. I didn't do this, Dr. Cleveland did, or either that or he took it somewhere. This is the derivation. How do we do this? How do we get it done? Is to sit there scratching your chin for a couple hours and try a whole bunch of things and think of this one. I'm not asking you guys to do that. I'm just asking you guys to understand, given that I'm saying let's do it, that it actually works. So let's take the log of the whole thing. What's the whole thing? It's this. All right, so we'll treat this as something. We'll call it, I don't know, t. I take the log of t. Can I take the log of t? Yeah, I can take the log of t. So let's do it. Take the log of the whole thing. How do logarithms work? Well, it means, well, that's not what it means. If I take the log of, I don't know, log of 3 times x, what do I want to do if I want to separate these? Well, it's the log of 3 plus the log of x. So that's how we get from here to here. I'm pulling this term out. That's where it comes here. And so now what we have is the log of the product. Now, what's the log of a product? Well, think about what we just did. What's the log of x times y times z? Based on what we just did here. What's the log of x plus the log of y plus the log of z? So log of x plus log of y plus log of z plus. Now, do we have a symbol? So if this means take the product of everything in my collection, do we have a symbol that says take these? I almost said it. Instead of doing multiplication, do addition instead. So I got a collection of stuff, add them all together. Well, yeah, we do. It's the sum. So if I have the log of a product, it's the same as having the sum of our logs. All right. So now that's how we get from here to here. We pull the product out and make it a sum. All right. So we're taking the sum of x raised to this power here. Now there's a nice little fact about logarithm and this constant here, and that they cancel each other out. See, it's not technically what they do, but that's the easiest thing I can explain. If you take the natural log of e to the x, you're getting x. It's like multiplying by 10 and dividing by 10, kind of. All right, so we don't have to deal with those anymore. So now all we need is whatever was in the power. So I've got the power, and that's this. All right. So I've done some stuff. I took a constant out. I took the product out, which turned into a sum. X I kind of left alone. And I took the log of something, of e raised to something. Okay, well, those cancel each other out, sort of. So let's do a little bit more. This is, one second, sorry. What we're going to want to do, spam callers driving me nuts, is we want to get this 2 sigma on the bottom of this. We want it to go away. So we're going to move this out. Notice we have to put it on every term here. Good grief, call me twice. So we move it out of the power, and we're separating the 1 over square root of 2, square root of 2 pi sigma. So this becomes this one here, and we're moving the 2 sigma out. So what does that get us in the end? Well, it gets us this term and this term, which is a product on x raised to something. All right. So that's how we get here. And I'll keep that on the screen. So let's rewrite the output of our line as a single value. So it's kind of like what I was doing before when I said, let's just call this thing t. Well, I'm going to call theta 1x plus theta naught. I'm going to call it, this isn't y bar. I don't actually, y hat, I'll call it y hat. So I'm going to make a new term. I can always make a new term. All I'm doing is I've got a big giant collection of stuff. And I want to, not change it, but I want a smaller symbol for it. So I'm going to call it y hat. Y hat is theta 1x plus theta naught. Well, I've got a theta 1x plus theta naught right here. So now I can rewrite that as this doesn't change. The coefficient doesn't change, but I have the sum of y minus y hat squared. If we want to remove the negative signs, let's recall that maximize, remember, because what are we actually trying to do here? I've got some inputs. I want theta naught and theta 1. I want to fiddle with them to get the biggest output I possibly can. Now I've got negative numbers here. Now what on earth am I going to do with that? Well, let's recall that maximizing a number is the same thing as minimizing the negative of that number. Why is that? Well, you take a number somewhere on the number line. So here's 0. If I want a large number, that means it's going to have a property. Let's call it y. So y times -1 is going to be it's going to be a large magnitude negative number. So if I, for some reason, have the negative of my number that I'm trying to make large, well, the further away it is from 0 in the negative direction, the larger the positive is. So let's do that. Because why do I want to do that? Why do I want to bother? Well, it's because we've got a bunch of negatives here. So we're going to, instead of maximizing, let's minimize the negative log likelihood. Now, what the heck is a log likelihood? Remember when we took the log of the whole thing? Why on earth do we do that? Well, it's because there's an e here and we want to get rid of it. But we took a log. And what happens when you have an equation and you want to do something to one side? You have to do it to both. Here we have the likelihood. Notice that the L changed. This is the log likelihood. It's just a symbol we use instead of putting log over here. Okay, so we can write our log likelihood like this. Oh wait, we're on the next one. So the negative likelihood is, let's minimize the negative log likelihood. That's what we have now. I have, let's call this term here. I don't know. I won't use X or Y. I'll just say A. And this term here, B. So I have something, some stuff equals minus A minus B. Well, there's a -1 in here somewhere. So F of some stuff is -1 times A plus B. If I want to, I could say the negative function is A plus B. So that's what we're going to do. So move the negative over. And now what we have is the negative log likelihood is this. Our ultimate goal is to find the parameters of our line. So to minimize the negative log likelihood, that's what we have here, with respect to the linear parameters, which is the thetas. Remember back to theta naught plus theta 1x plus theta 2x squared, but we don't have any x squareds. Theta 1 is where we stop. We can imagine that our variance term is a fixed constant. It's what we did earlier. So the variance squared is fixed. It's not changing. Why is it changing? Two things. One, everything is well, I guess the first one kind of implies the second. They're independent and identically distributed, and it's from a Gaussian distribution. So we can imagine our variance term is a fixed constant. If we remove constants, which don't include our thetas, this won't alter the solution. Therefore, we can throw out any constant terms and elegantly rewrite what we're trying to minimize as the following. So let's imagine for a moment, as I was saying, if you have inputs to a function and that input never changes, it's a constant. So if it's a constant and it's an input to a function, why is it even there? Well, there is an actual reason for it, but let's see what happens when we get rid of them. So let's get rid of this one and that one and that one. Well, if we can get rid of one constant, why not just not look at the other constants? Because we're not so much interested in the exact output of this. We're interested in fitting it to a line. What happens if we don't? Well, instead of, let's say, getting rid of them, let's call this C1 and C2. Well, the term of interest is right here now. C1 and C2 never change. This is the only thing that changes. So what we have now is this. Where have we seen that before? Well, let's think back to what on earth is y bar? Remember, or y hat? We made something for that, right? It's theta 1x plus theta naught. So if we take the true value of something and subtract the estimate we have for it, and then we take the square of it and sum that together, that's kind of the sum of the squares, right? Sum of the squares of the errors. So it turns out that the maximum likelihood estimate for a linear model is the line which minimizes the sum of the squared errors. Didn't we just spend like an entire 2 labs and 2 lessons trying to minimize the sum of squares? That's interesting. The entire point of that is to show that really we've been doing this all along. Now let's solve for parameters. We've concluded that the maximum likelihood estimate for our slope and intercept can be found by minimizing the sum of the squared errors, which is what our linear regression does. Let's put stuff back in to our objective and use it as our index over some points. So instead of using y hat, let's plug the stuff back in. So we're summing over our points. You have the measurement minus your theta 1x. So this is your input variable minus theta naught, which is a constant. And you square the whole thing. The square in this formula makes it quadratic with a single minimum. The minimum can be found by taking the derivative with respect to each of the perimeters and setting it equal to 0. You guys had calculus yet? Okay, so I don't need to explain why that's a thing. And I suppose by explain, I mean really go in depth. We've got a parabola with a single minimum, and it's going in this direction, meaning it opens upward. And where's the minimum? Well, it's the point right here where where's my tangent line at this point? It's flat. What's the slope of a flat line? 0. So set my derivative to 0 and find where it is. So we can find it. Can we find it? Yes, we can. All right. So we take the partial derivative with, that's weird. You'll have to ignore the dog. Somebody ring the doorbell, which is strange because I don't ever get visitors here. All right. Setting the derivative equal to 0 and solving for our intercept can get us the intercept. Taking the partial derivative with respect to the slope gives us the other one. So I don't know partial derivatives. I think it's Cal 3. I don't think you guys have had that. But basically here is the reason we can't just take a regular derivative. I got two things I want. Okay, well, take the derivative. Take the derivative of what? You can't just take the regular derivative in this case. It's got to be a salesman. No one rings my doorbell twice. Sorry, you guys are gonna have to deal with that. So if I want theta naught, I have to get rid of the theta 1. And in order to get my theta 1, I have to get rid of the theta naught. Now theta naught's just a constant in this, so that part was easy. But so I take my derivatives to solve for this one and solve for this one, and now I have some data. Well, data is a bad word because we're talking about data, but I have my coefficients. I have theta naught, I have theta 1. Y is the output, X is the input, so I have everything I want. I have variables and coefficients. Let's put it all together. My function, finding my line. We have a collection of X, we have a collection of Y. How many points are there? Well, let's figure out the length of X. Let's calculate the sums. I'm sorry, let's calculate the mean. So we get the sum of each and divide by n and calculate the slope. So we're going to be doing a over everything. We're going to be adding stuff up, and then we're going to divide to get the right number. So we have the entry in our X minus the average times the entry in our Y minus the average. And for our denominator, we just want the X squared. This is what we've been doing quite a while. This is the sum of, you've got, instead of having the square on top, you've got the X and the Y, and on the bottom you have just the X. Finally, take the numerator, divide by the denominator, and we have our estimate for the slope. Now that we have that, we can calculate the intercept, and we return the slope and the intercept. All right, let's try using it. Let's look at the problem from exam 2, which is also an example in the previous lab. We had a table of recorded times and speeds from some experimental observations. Use the function we were just talking about to find the intercept and the slope. So here's our predictor variable. Here's our output variable. Okay. We have the numbers from our y, the numbers for our x, and we're going to use the function we just made. And it predicts the following. Slope. I'm really sorry for the dogs, guys. We have the slope of about 12 and intercept of about -16.5. So that's where our line's going to go. Well, let's plot that out and see what it looks like. Looks kind of like that. Have we seen this before? Have we seen something that looks like that? I think we have. That looks very similar, doesn't it? Almost as if by trying to maximize the best fit. I'm really sorry for this. I have to step away for just a second. I'm sorry, there's someone banging at my back door now. Sorry. All right, I'm really sorry about that. And you'll have to deal with the dogs. There's an exterminator outside. Okay, so the reason we took all this time to draw a nice line on some plots here is to show that doing the maximization for likelihood, same thing as minimizing the error in squares. So now we are actually equipped to talk about how well fit this is. So far, we've assessed the quality of these fits visually. We can make numerical assessments as well via the goodness of fit measures. Let's discuss 3 of the most common metrics for evaluating predictions on regression machine learning platforms. So how can we say how close is close? Good question. I'll give you some textbooks and a weekend and a whole bunch of coffee and come back to me with a good answer. Your answer is probably going to be one of these 3 because they're very commonplace. So the first one we're going to look at, can you guys see this formula? Do I need to shift back to blind mode? I'll do it. It's fine. Okay. The first one is mean absolute error. It's the average, and these are less important that you have to understand the derivation and stuff like before. It's just you need to know what they are and kind of what they do. You can just plug and play with the equation. It's the average of the absolute differences between predictions and actual values. It gives us an idea of how wrong the predictions were. The measure gives an idea of the magnitude and the error, but no idea about the direction. Here's the formula. Now, well, what does that mean? Well, if I take the absolute value of something, the function for an absolute value kind of looks like this. So if I get, is it a function? I think it is a function. If I get a value of, let's say, 5, well, was it this one? Was it the value that put me here, or was it the value that put me here? I don't know. Was it the negative version or the positive version? Don't really know. All I know is it's the actual, or it's the measurement of the error. Okay. So the arithmetic average of the absolute errors, where yi is the prediction and xi is the true value, is known as the scale-dependent accuracy measure, and therefore cannot be used to make comparisons between series using different scales. So let's calculate manually. Let's see. We have the values we had before, speed, and our y prediction. Let's take the mean of the absolute value and the differences. That's what we've got, the actual value and the prediction. Yeah, and we're going to print it out. Looks like this. So results by manual calculation gives us this. And then we have the actual, you don't need to do this every time. sklearn has a mean absolute error. I'm surprised it doesn't use the acronym. So how close were we to it? Well, as far as the decimal points go, we were right on the money. So pretty much you know how that works now. We have the mean squared error, which is another one. This is the one I'm most familiar with. It's much like the mean absolute error in that it provides a gross idea of the magnitude of error and measures the average of the squares of the errors. That is the average squared difference between the estimated values and the actual value. It's a measure of the quality of an estimator. It is always non-negative, and a value closer to 0 is better. MSE of 0, meaning that you have perfect predictions, is ideal, but you're only going to get epsilon of 0 in like the how to explain this. If you get an error of 0, alarm bells should be going off in your head saying someone cooked up this data. Almost any data you find out in nature or whatever, it's kind of strange to say that data is out in nature, but you know what I mean. Outside the laboratory is what I guess is the best way to say it. If you get a delta, or I'm sorry, an epsilon of 0 outside the lab, you should be suspicious. So taking the square root of the mean square error converts the units back to the original units of the output variable and can be meaningful for description and presentation. This is called the root mean square error, the most widely used metric for regression. And here's the formula. Now, the reason I'm most familiar with this is that line right there. It's the most used one. Now, why do we have two things in one line? It's because you remember back to variance and standard deviation. I get a variance of 61. What the heck does that mean? I don't know. But I get a standard deviation of 12 meters per second. Now that I can visualize a lot better. Same thing here. Mean squared error doesn't have any units. But the root mean squared error has the same units as it did in the data. And it's, let's say you're giving a presentation on data. And in data science, it's kind of a job. Like I'm not talking like a school presentation. People who you're tasked with, you've got a million bajillion points of data, present it to the people who make decisions and make us be able to understand it. It's going to be part of your job. If you show them the mean squared error, all right, mean squared error. So how close were we in closeness? It's 71.312. What? Oh, I mean, here's the root mean squared error. $6.1 million on either side. Oh, okay. Much more easy to digest. All right, here's the formula. We can make it manually, and we can also use the mean squared error. I suppose that's why the acronym is not used. All right, so here's the thing for our data. We were talking about speed, so this will be in meters per second. So the mean squared error is 108, 109-ish. The root mean squared error is 10.43 meters per second. And the same thing calculated from the package. So we are exactly as accurate. All right. The last one we'll look at is called the R-squared metric. I can't remember if this is where R gets its name. It provides an indication of the goodness of fit of a set of prediction to the actual values. This measure is called the coefficient of termination. This is a value between 0 and 1 for no fit and perfect fit, respectively. It provides a measure of how well observed outcomes are replicated by the model based on the proportion of the total variation of outcomes explained by the model. This one I'm not actually familiar with. So let's see. What does it look like it's doing? The total sum is going to be sum of the measured minus the average squared. The residual is going to be the measured minus some term we have here. So we're calling this the error, all right? And then we're going to take 1 minus the residual over the total. So if the residual is small, what would that make R squared? If the residual is small, what does R squared approach? What's a residual? While you guys answer that question, I'll show you what a residual is. I've got a point, right? And I estimate it. You know, I don't know exactly what the point is, but I estimate it. And I get my estimation about here. Well, I missed. Now, how big is this scale? I don't know. This could be tiny, it could be huge. But the miss is the residual. So if I have a fraction here, what happens if my residual is very, very small? What happens to R squared if my residual is small? Well, see if I can spell it out a little easier. It's bigger? Yes, it is bigger. What does it approach? I have 1 minus A over B. No. Yes, it approaches 1. What happens when A goes to 0? Well, I get 1 minus 0. 1 minus 0 is 1. And as we said before, perfect fit is 1. And a terrible fit is 0, which means this can go from 0 to 1. Well, how on earth am I getting r squared to 0? Well, if the residual becomes the actual total measurement, it means your error is just as big as how far you're measuring. You get 1 minus 1, and you get an r squared of 0, meaning you have not made a fit at all. All right, let's plug that in and compare it to the one we have in metrics. Same thing, all the way out. All right, so that, you'll have to forgive me for a lot of things in this lab. One is very mathy. I did my best to make math fun and interesting, but there's only so much you can do. Two, the dogs and me having to step away. It's unacceptable, but I did the best I could. So let us look at a exercise and the homework. We've got about 10 minutes left. So everything you're going to be doing in the homework, as has been the pattern, is going to be stuff we've been doing in, I believe, the previous 2 labs, but it's going to be, that's where you're going to be looking at. All right, so you have a CSV file. It's got the recordings on daily temperature, relative humidity, and cone strength and cone weight based on the noon readings for 20 days of cone making. So what kind of cones are we talking about? Ice cream cones. When do they fall apart? Do they fall apart? Do they crumble? Do they get soggy? That's what we're trying to figure out, because we're in the business of making ice cream cones. Follow the following steps and answer the following questions. So what do we got here? We have scaffolding. Hooray. Read the CSV into a data frame. Explore the data frame, and in a markdown cell, briefly describe it in your own words. How do you make a markdown cell? It's pretty easy. Make a new cell, change it to markdown. All right, calculate and compare the correlation coefficient of the cone's weight with all the other parameters. In a markdown cell, explain the results and state which parameters have the strongest and weakest relationship with the cone's weight of a vehicle. What do we mean by a vehicle? Wheel. This transports the ice cream. Step 3, use linear regression modeling. Use stats models. You don't have to. I suppose if you reprogram all of them, I don't recommend this at all. I'll be impressed enough to probably not take any points off. But my advice: use the library. Get the linear model's coefficients. Make a plot and visually assess the quality of the linear fit. So that's going to be kind of what we've been doing up to this point. Is it good? Is it bad? I don't know. Draw a line. It seems okay. Step 4, do the same thing with stats models. So I guess, oh wait, never mind. Get the linear model's coefficient, and now you're going to visually assess, and this is for, what's the difference here? Yes, cone's weight and humidity, as opposed to cone strength and cone's weight. Got it. So you're going to be doing the same thing with 2 different points. So visually assess the linear fit for the humidity versus weight and the strength. Step 5, use multiple linear regression. There's an example of this in 19, I think. Pretty sure it's 19. And use all 3 predictor parameters to predict the cone's weight. And then do the same thing we've been doing before. Explain the result in a markdown cell. As a conclusion, make a statement about the quality of the 3 predictive models you wrote and compare their performances. Now notice this part doesn't say visually assess them. It's almost like we've developed a method to really say how close is close. And there's 3 of them. Okay. So we have 5 minutes. I don't believe that's enough time for me to get through this entire exercise here. So what I'll do is I'll say, are there any questions? Number 1. Number 2, Dr. Cleveland, is there anything you want to announce or anything? And if the answer to both of those is no, then I'll go through what I can.
Yeah, I just want to remind everyone about putting together their teams so they can do the semester project. I've got I think there's almost 24 or 30 or something. So there's only 20 of you left that have not teamed with anyone, and just use the Blackboard to help you pick a team, because I think you can email each other through Blackboard. That's it.
Okay. All right. So this is a very mathy lab. And I remember how it was undergrad. And heck, I was a math major and calculus too. I sit there with my eyes glazing over. So
Yeah, on this particular example that's in front of y'all, don't code it yourself. Use Skylearn and SkyPy and any of the other packages we've discussed already to help you do these parts. You have to use the mighty GoogleNet, given the time, sure. But
so
do not write your own script for this. Use as much external package as you can.
actually, a solution to this problem. I don't know if you guys, I haven't seen anybody from this class there. This is the reason I don't know. They set up tutoring for this course, and mine is today at 5. So if you guys show up, I'll do this example then. Because I don't want to rush it, and because I want to show the process of, all right, I got to do this, look up the function, look up the signature, see what it does. And that'll take, I don't know, 10, 15 minutes. So,
So are we gonna, is this homework, this last part?
well, yes and no. You need to turn in the lab itself, but it's not actually on the homework. But everything here, I would say it's in your best interest. It's probably going to show up on an exam. But as for strict homework, no, I don't think it is. It's part of the lab. You do have to turn in the lab though. I'm not going to be harsh though, like on grading, because I didn't get enough time to go through it. So hopefully that answers that. What was I going to say? Oh, right. Yeah, the tutoring thing. If anybody does not have the link to that, let me know, and I'll send it out in the email. But yeah, any questions on the homework or any of the stuff we've gone over? I know it was mathy, but in a sentence, what did we figure out? Well, if we want to get as close as we possibly can, it turns out we end up minimizing the sum of the squares and the differences of our measured data and our estimated, which is what we've been doing all along. So I don't see any questions, meaning I'm assuming everybody has the link to the session. So that's good. All right. Well, if
All
no
right.
one has,
Well,
yep.
we will hang up in like,
I have one more question. As for the project, what else should we like plan to get done for this week?
It's an excellent question.
well, if you take a look on the project statements, it gives you guidance to help you answer that question.
Is that just on Blackboard?
That's how you get to it. So you would go through Blackboard to the projects.
My Blackboard's not loading right
Reclaim
now.
the machine.
Yeah, I gave you host. I was going to share it, but mine's stalled. It's not loading.
Is it on the content server?
Yeah, hang on a second. So we go to project teams, and let's get up to the web root. And the projects that you have to choose from are these three. Do not do all three. Your team picks one. By all means, pick the one you think is going to be the easiest for you to do well at. And it has the specific tasks and the deliverables. And so each week you would submit an effort sheet that's with every team member. So I would say for this week, for the teams that have been assembled, you'd say we put together the team, we set up one meeting. And then just before Thanksgiving is an interim report. It doesn't have to be complete, but this is where you're going to break down the project tasks and who's going to do what. And then finally, on December 7th is the final report with your completed project.
Okay, and is there gonna be a submission thing on Blackboard for the effort sheets every week? Or do we just email that to you?
See, there's like only 14 teams. Yeah, just email those.
Okay, thank you.
Okay, that's all for today. Everybody have a good weekend. No, is it weekend time? It's Tuesday. Hey, I'm getting a little bit ahead of myself. Have a
Time
good evening.
changes.
Have a good afternoon, rest of the day, and I'll see you on Thursday.
Thank you all.
Bye-bye.